Hi, everyone. My name is Jesse Galef. I'm part of Etienne's team with the machine learning R&D, generally doing machine learning and hoping to focus on interpretable machine learning. I've been with the company for a little less than a year, so I'm still pretty new and really enjoying the work. So I'm going to talk about some of our current tools that we have and some of the tools we're developing right now, and hope to get some questions about how you would like to use some of the interpretation tools. So let's get started. The thing I love about machine learning is that it is too smart. A surprising amount of my work in neural nets previously was about convincing them to be stupider and to focus on the patterns we wanted them to. This is an example I really like, that there was a team trying to predict pneumonia from X-ray scans, and they found a lot of images from different hospitals and trained a convolutional neural net, which focused on patterns in the images and did a really great job until they tried to figure out why they were doing so well. And it turns out that the neural net was picking up on particular tokens and symbols indicating which hospital the scan was from. And some hospitals do a lot more treating of pneumonia. And so it's possible and very plausible that the machine learning is picking up on a pattern you don't actually care about, or that it's not going to replicate in the real world. Or it's picking up on something illegal, or picking up on something that is not causal. Or maybe it's picking up on something that is really exciting and a new discovery. But without having a human in the loop to look at the findings, it's hard to know quite what to make of the patterns. So the general approach that people like to talk about is to have a human in the loop, looking at the findings of the model and sort of tweak it, try it again. So we both want to know how well the model works and how it works. So what does it do well? What does it do badly? So we can find maybe doing some feature engineering to correct some of the problems that it's having with particular classes. What does it do suspiciously well? So sometimes the answer bleeds into the training set, and you don't want it to find the answers. I think one case, the machine learning model discovered that it could tell that alternating images was the answer, because the people didn't randomize their test sets or the training sets. But yeah, we want to work with the machine learning models to help them help us, and possibly explore data and learn new things, because they're very good at spotting patterns. We are good at providing context. But let's get right into it. I mean, starting out, interpretable models. We should use models that can be easily interpreted if we think they'll work. And a lot of the time, simple linear regression, logistic regression will do a great job, and they're simple to understand. The tools that we've been working on in the machine learning team with predictor and classifier measurements allow you to understand a little bit more how the model is handling the data. We can check information. And what I've been working on, SHAPValues, is going to be new for 12.2. And I'm going to talk about how it can be used on single examples to explain a decision, how it can be used to sort of explore a model and understand why it's doing what it's doing, and then get into some of the philosophical questions behind what we mean by an explanation and causation. So that's when some of the interesting questions arise, and I need to hear how people think we should proceed. So obviously, I'm going to walk through an example here with a sample data set, the wine quality, where you have lots of information about different bottles of wine and you're predicting their quality. It's very simple. I love this one line, say, hey, predict the quality of the wine. And 2 lines or something is really good. I'm specifying a linear regression, because if we then call information on it, we get a handful of information. We can look at the learning curve, so how well it's doing with different amounts of training data, but also we can just ask for the function and see exactly what it is doing. It is a linear model. Each coefficient is multiplied by the variable for the bottle of wine. And this isn't standardized. If we made each variable mean 0, standard deviation 1, then the magnitude of these coefficients would be how important the feature is. And that's very, very handy, very simple. And there are all these other properties that you can use from the information to get a sense of the model, but not how it interacts with data. That's the next set, the predictor measurements. So you notice the previous part with information, you didn't need a test set. Here you provide a test set, the predictor, your model runs on all of it, and you get to see how it did. So you create a predictor object, just call it and ask for the R squared or the mean square. It automatically provides, this is a comparison plot, which is the predicted value versus the actual value. You can see generally how it's doing. And there are a ton of other properties that you can ask for. I think some of these, you can just ask for a residual plot and see how well it does at different predicted values, or take the residuals and plot the residuals against the values themselves. So here's an independent variable, the total sulfur dioxide. And just by looking at it, we can see that the residuals, so how far the model is off in its prediction, are much higher in the middle compared to the edges, indicating that it's doing a good job at high and low amounts of sulfur dioxide, but in the middle, it's getting things wrong. And that makes us think that maybe the feature isn't linear. Maybe we should get a non-linear model. It's pretty useful to be able to poke around and see these things, and especially so easily with the Wolfram predictor measurements tool. And I'm not a wine expert, so I don't know if this is what we can learn from this in particular, but noticing which predicted examples are the worst, so which it had the hardest time of, maybe we can notice that it is doing a bad job with all of the high sulfur dioxide wines, and we can try to feature engineer to help it out. But without knowing wines, that's not something I can really weigh in on easily. I'm not going to spend much time on it, but classifier measurements is very similar. You can train a classifier in no time at all, and then the classifier measurements object will provide a similar report, but instead of a comparison plot, has these confusion matrices and has more properties about classification and accuracy and F1 score and area under the curve, things like that, that are very standard for understanding how well a model is doing and which things it's doing well and poorly. Which brings to the SHAPValues. This is what I've been working on, and I'm sorry I didn't make the acronym, but it's SHapley Additive Explanations. The P from explanations is the last one, and it's a very meta acronym, or I guess, yeah, acronym, not initialism, referencing Shapley game theory concept, which is Lloyd Shapley won the Nobel Prize in economics for this in 2012, which is a way to attribute credit or blame in a group. And it's used fairly recently. I think it was 2017. Somebody wrote a paper on this, that you can have a model agnostic approach where each feature you want to attribute credit to the feature for how much it does or doesn't affect the prediction. And it doesn't matter what the model is. We don't need a linear model. We can put anything in as long as you can give it an example and get the result, and give it a handful of different examples and see how it affects the model's predictions. Let's walk through an example of how it would work. Let's say we are not restricting ourselves to a linear model. So again, we're going to do a quick training on and specify a random forest, which is notoriously hard to interpret. This is not linear at all. And train it, and we can see that the R squared is significantly better than the linear models. The mean squared error is significantly lower than the linear model. So this is doing better, but it is hard to interpret it. So we need some understanding. Let's pick a bottle of wine, bottle 42. And again, not knowing very much about wine, it seems like a fine bottle. The true wine quality was 6 out of 10. It's a little above average, I think, or I forget what the exact average is, but oh no, the average of all bottles in the set was 5.8. So this is slightly better than average, but so our model, on the other hand, which is not perfect, predicted 5.2. Why? That's the question that we want to answer. And all we need to do at the moment is call the predictor with the property SHAPValue. So just like we would call it on an example asking for the answer or the probabilities in a classification, we ask for the SHAPValues and get back these numbers for each feature. So it's saying because of this model's fixed acidity of 9.2, the model boosted its prediction by about 0.05. Because of the volatile acidity of 0.34, it lowered the predicted quality. So you can do this for each of the features and get a quick chart for how each feature impacted the final prediction, and see that residual sugar was very helpful for improving the wine quality in this context, and the alcohol and density were very bad for it. The thing about SHAPValues, Shapley Additive explanations, is that they add up to the difference between your prediction and the mean. So the total of all of the SHAPValues for this model are negative 0.61. And we can look at if you take the mean value of all the wine quality and add that, we get very close to what the model actually predicted for our bottle. So since it's additive, it's possible to make a little plot like this, which I don't know, I enjoy to use the step plot where it starts at the average perhaps, and then because of the density, it lowers its prediction, and then because of the alcohol, lowers its prediction, but the residual sugar boosts its prediction back up, and it sort of winds its way and converges on the deviation from what it would say at the middle for the mean wine quality. Again, not going to spend too much time on how the classifiers are different, but it's very similar. You just call it as a property for SHAPValues, and it returns the log odds ratio. So calling it on the Titanic dataset, asking whether somebody's likely to have survived. If the numbers are negative, it harmed their chances of being as part of this class. So we look at the odds ratio for this person being in first class, boosted their odds by 5. So if it was a 2-to-1 chance of surviving, now it's going to be a 10-to-1 chance of surviving because of their class. So those are each one example at a time. But if we do it on a number of data points, we can start getting an overall picture. And so here, called it on all 500 data points in our test set. Takes about 20 seconds. That's it's going to be reasonable, but it's not instantaneous. We've actually found ways to simplify it quite a bit, but you can get feature importance by just taking the absolute value of the impact. This is something that is common in random forests, and we can predict the feature importance in linear models very easily. But neural nets make it kind of difficult to assess feature importance. And so using a SHAPValues of a number of examples can help you get the sort of the overall importance of a feature. Or you can start plotting the feature values versus their impact. So we can look at different fixed acidities. What was the impact of the acidity for this bottle? And it's, as the acidity goes higher, it starts being a very bad thing, always in context. So this is a particular bottle and a particular volatile acidity, citric acid, everything else. In that context, the fixed acidity hurt its prediction. And we can see lots of nonlinear predictions. So we can understand more of what our random forest is doing. A random forest seems to be using the 0.27 or something value, at which point it starts rapidly penalizing the prediction for based on the citric acid. We can see, oh, interesting, sulfur dioxide might be a little bit zigzag or cubic, but we can also look at interactions between the different features to see that only in high alcohol cases does the density being high help the prediction. So these are things that are, once you get to play with them, gives you a real chance to look at how the model is doing what it's doing and possibly explore and find some new principles that are new to you as a wine scientist. So what are they? How they work, the theory. So I was describing how important it is that these are in context for the bottle of wine. And we can't just change the density, feed that into the model and see what its new prediction is, because what if it is only important in combination with a particular acidity, or having an alcohol content of 8 or this density makes it a particular prediction, and changing the density isn't going to affect our model's prediction yet. So Shapley values, this is the game theory thing that got the Nobel Prize, looks at every combination of whether or not you know or don't know the feature, change it or don't change it. So if you know the alcohol and acidity, you look at the prediction versus if you know the alcohol, acidity, and density. If you know the acidity versus knowing the acidity and density. So in every case, you see what it's like with or without this particular bottle's density and look at the prediction. I found a pretty decent illustration. This is for predicting the income from age, gender, and job. And in each case, you want to judge how the model's prediction changes when we add in the feature age. And adding it all up in a particular weighting system, which is the Shapley discovery or development, we can explain the difference between the mean with no features known. If you don't know anything about the person, we predict 50K in this model. And if we know their age, gender, and job, we know that we predict 83,000. And we need to know how much is just age. So we look at it as we add in age. This is where it starts to get philosophical, but what do we mean by changing the feature? It's not clear. There's discussion and there are pros and cons of different approaches, but let's take a case where we're trying to predict heart attack risk from age, blood pressure, and salt intake. So here's a man, 72 years old, has very high blood pressure, I think. I think that's very high, and has a high salt diet. And our model says that the risk of heart attack was high. And we want to know what the impact of blood pressure was. There we go. And so the first approach is asking the model to infer the blood pressure. This is the observational approach. So we could ask the doctor, without mentioning the blood pressure, what do you predict for a 72-year-old man who has a high salt diet? And the doctor says, well, given the high salt diet, he probably has high blood pressure, so he's high risk. And then you say, what if I told you his blood pressure and it's high? She says, yeah, that's what I expected. He's high risk. So because those predictions aren't very different, giving the model the actual blood pressure or not, it'll attribute less impact to blood pressure. So even if blood pressure is really important in the model, if you can predict the blood pressure from his high salt diet, then the impact is spread out among those different features. And that's a little bit weird to think about, the idea that the model might not use diet at all. The model might only look at blood pressure, but because blood pressure is, because the diet is useful for inferring blood pressure, it's still given impact. So this is considered being true to the data, but not necessarily true to the model. When would you want this? Well, proxy values are pretty important in understanding the legality and fairness questions. If your model doesn't use race, but you discover that it, when race is included, you can learn that it is predicted that zip code is the classic case, but zip code in theory might not matter. But if your model is using it as a proxy for race, then we can look at it and say that we need to revisit our model and the legality of it. So the second approach is the interventional, asking the model to change blood pressure and see what it says now. So you ask the same question, with 72 years old, high salt. The doctor says that he only looks at blood pressure and high risk. You say, cool. What if we could get the blood pressure down to a good amount. The doctor might say, oh, great, low risk. And if you ask if we could change his diet to low salt, but he still had high blood pressure, doesn't matter. Blood pressure is the thing that matters. So in this case, looking at the differences as we tell the doctor his blood pressure or don't tell him blood pressure, or tell him a different blood pressure, it's very different. And so because the model relies so heavily on blood pressure, we understand its impact. This is true to the model. And even if the salt diet is useful and important for understanding it in the real world in a causal sense, the model might not use it at all. So this is understanding more, it's being true to the model, they say. But has some downsides as well, where you're not going to discover proxy values, and it might test your model on ridiculous data. So you're not, I mean, it's one thing to say, hey, maybe we can give him blood pressure medication and reduce his blood pressure. But that requires human context, and it's not always easy to know which values are sensical. We're deliberately throwing out our conditional understanding of the patient and accepting some interventions. So we might ask for the risk of cancer for an 18-year-old given 22 years of taking hormonal birth control. I mean, it's just not, the model might not work very well in those contexts, to say the least. So these are the general approaches. At the moment in 12.2, we're going to be implementing the observational approach. So inferring blood pressure. So understanding your how the model sees the world. It's very metaphorical and personifying, but trying to understand how the model understands the data. And so even if a feature isn't immediately used in the model, if it's important, then you'll understand it. And this is part of the, one of the things that Wolfram models have. It has an imputer for missing values, and it's going to be better and worse at predicting missing values based on its understanding of getting a large data set, which is very true to machine learning. So we're trying to choose how to proceed with some of the philosophical questions and how important it is to have the interventional SHAPValues to know what applications they're going to be used for. And so I think I have it as a poll in the Pathable. So I'd love to get your input on how you're likely to use SHAPValues. I should have given a free answer, and I'm sorry for that, but I'd love to hear in the Q&A and in the chat for questions for how it can be used and how you have an intuition about what things you're hoping to learn from your models. I think that is beyond my, yes, that is a little beyond my time, but I can take questions. I can check the Pathable chat and see. Oh, I'm seeing some both interventional and observational. I think they're both really cool. And the more I think about causation and correlation, it's very, very tricky. Judea Pearl's do calculus, as he calls it, is the question: if we do this to the world, what happens, rather than looking at just correlations. But since models are so correlation-based, machine learning models are looking for correlations, and it's very hard to sort of imbue them with a sense of causation. So it's, I think the observational approach is the one that we went with first, and that is the easiest to explain in terms of the model. But yeah, it's really, it's not straightforward, to say the least. There's still discussions about it. So the real world data is expensive. We often don't have as much of it as we would like, always. So we work with what we have, but worry that our model pays too much attention and overfits the data we have. Yeah, I don't know. Let me think about the best approach for that. I do think even the predictor and classifier measurements will do a decent job of helping you understand your model's strengths and weaknesses. The Let me actually go back to it, but the model, these, yeah. Is this bad? Yeah, let's go back to the information. So one thing that is helpful is that even in a single line call, forming a predictor model, it's trying a number of different algorithms with different amounts of hyperparameter tuning and regularization. And if you don't specify which method, so I deliberately said, hey, you have to use a random forest here. If you don't, then it will use cross-validation to pick these things and find what's best, which is, I mean, without a ton of data, it still says, put some aside, train on part of it, and then check on the part that it held out repeatedly to get a sense of, if you can't train on this exact data, how well can you predict? It's, I mean, you're still limited to the data you have, but if you can figure out which data is important and which features are important, then you might be able to do a better job and spend your time focused on the things that are the most helpful. Yes, SHAP can be used for classification problems. I'm hoping that my computer can handle it, but let's see the SHAPValues example for, yes, so here's the case with a classifier trying to understand why this particular person was given a chance of survival or not. Let's say classifier. So we can look at the first person's, we can actually look at both the probabilities and SHAPValues. I think, let's see if this works. Yes, okay. So the probabilities of survival, the model itself gave them quite a good chance of surviving, 85%. And we can look at the survival, the impact on their survival. So these are the log odds ratio. Positive is good, and we take the SHAPValues and take the exponent of them, then these are the log odds ratio. So I think the average survival was about 1 to 2 for about a 30% chance of survival, something like that in this test set. And so if we take, well, let me actually look at the mean. Oh, that's what I want. This is not the best use of our time, I'm sorry. All right, fine. All right, but if it's about a 30% chance, then that's odds of 1 to 2, which is 1 through 3. And then we multiply by about the 5, which is what the class does for us, and multiply by 0.78 and multiply by 2.3. And so these are the odds of survival, about 3 to 1, which is about 75%. And as just rough estimates, a 3 to 1 odds, 75% is very close to what we predicted. Yeah. Cool. I'm seeing neat conversation even happening in the chat. Generative Bayesian models. Let me think. I think it'll be interesting to see how the Bayesian models handle intervention. I mean, it's still a question of intervention versus observational. So how much we are allowing things to intervene versus look within the data that we already have. So I don't know that there's a way out of it, but if you know that you want observational SHAPValues, then I think Bayesian models come with a lot of priors that are really useful and might make things really quick to use. Right. I am a little bit over time, but appreciate everybody coming, and feel free to continue in the chat. I will be around to see the questions, and feel free to email me, jesseg@wolfram.com. And otherwise, have a great rest of the conference.